The formation of star systems is a complex process that begins deep within vast clouds of cosmic dust and gas. Over millions of years, gravity pulls these particles together, gradually giving birth to new stars. Surrounding these young stars, disks of dust and debris begin to coalesce, eventually forming planets and other celestial bodies. Understanding how planets emerge from these cosmic materials is crucial for unraveling the mysteries of our own solar system and the origins of life. By studying these processes, scientists gain valuable insights into the evolution of galaxies and the potential for habitable worlds beyond Earth. This knowledge not only deepens our appreciation of the universe, but also guides future exploration and discovery. Cosmic dust originates from a variety of sources, including dying stars, supernova explosions, and the outer atmospheres of red giants. These tiny particles are composed of elements such as carbon, silicon, oxygen, and iron, often forming complex molecules and minerals. Within interstellar clouds, cosmic dust plays a crucial role by absorbing and scattering light, which affects the temperature and visibility of these regions. It also serves as a surface for chemical reactions, helping to form new molecules, including those essential for life. Over time, dust grains can clump together, contributing to the formation of planets and other celestial bodies. Thus, cosmic dust is not only a remnant of ancient stars, but also a key ingredient in the ongoing evolution of the universe. In the vast expanse of space, clouds of dust and gas drift silently, often spanning light years across. Over time, regions within these clouds begin to contract under the influence of gravity. As the material gathers, the density and temperature at the core increase steadily. This process leads to the formation of dense clumps known as protostars. During this stage, the protostar is still enveloped by the surrounding cloud, continuing to accumulate mass. Eventually, as the core becomes hot and dense enough, nuclear fusion may ignite, marking the birth of a new star. Protostars are the earliest stage in the life cycle of a star. As clouds of gas and dust collapse under gravity, they form dense cores that gradually heat up and begin to glow. Over time, the protostar continues to accumulate material from its surroundings, increasing in mass and temperature. When the core becomes hot enough, nuclear fusion ignites, marking the transition to a young star. During this process, the surrounding disk of gas and dust flattens and begins to coalesce, creating a favorable environment for planet formation. The energy and winds from the young star help clear away excess material, allowing planets to take shape within the disk. This dynamic transformation sets the stage for the development of planetary systems. A protoplanetary disk is a rotating disk of gas and dust that surrounds a young star. Its structure typically consists of a dense, flat central plane where most of the material is concentrated, gradually thinning out towards the edges. The disk is primarily composed of hydrogen and helium, along with heavier elements and compounds such as silicates, water ice, and organic molecules. These materials provide the essential building blocks for planet formation. The disk plays a crucial role in gathering and distributing matter around the young star, enabling particles to collide and stick together, eventually forming larger bodies like planetesimals and ultimately planets. Over time, interactions within the disk shape the architecture of emerging planetary systems. In the early stages of planetary formation, tiny dust particles within the protoplanetary disk begin to interact. These microscopic grains collide gently due to the movement and turbulence present in the disk. Over time, repeated collisions cause the particles to stick together, a process known as coagulation. As these clusters grow larger, their increased mass allows them to attract even more material through gravity. Gradually, the accumulation of dust and small rocks leads to the formation of larger bodies called planetesimals. This step-by-step growth is fundamental to the eventual creation of planets and other celestial objects within the disk. The formation of planets begins with tiny particles of dust and ice within a protoplanetary disk surrounding a young star. These small grains gradually stick together through processes such as electrostatic attraction and collisions, forming larger clumps known as planetesimals. Over time, planetesimals grow by accumulating more material, a process called accretion. Several factors influence this growth, including the density and composition of the disk, the temperature, and the presence of turbulence. Gravitational interactions also play a crucial role, as larger bodies can attract smaller ones, accelerating their development. Occasionally, collisions may fragment planetesimals, slowing down the process, but overall, these interactions drive the emergence of early planetary bodies. In the early stages of the solar system, countless planetesimals, small solid objects formed from dust and gas, drifted through space. These planetesimals frequently collided with one another due to gravitational forces and random motion. With each collision, some planetesimals merged, gradually growing larger and more massive. Over time, repeated impacts and mergers allowed these bodies to accumulate enough material to become protoplanets. As the process continued, the largest protoplanets eventually evolved into fully formed planets. This cycle of collision and fusion played a crucial role in shaping the planets we observe today. The formation of giant gas planets is a fascinating process that sets them apart from rocky planets within a star system. Gas giants, such as Jupiter and Saturn, typically begin as solid cores that accumulate vast envelopes of hydrogen and helium from the surrounding disk of material. Their immense gravity allows them to capture and retain these light gases, resulting in their massive size and thick atmospheres. In contrast, rocky planets like Earth and Mars form closer to their star, where intense heat prevents the accumulation of volatile gases. These terrestrial planets are composed primarily of heavier elements such as iron and silicate, giving them solid surfaces. The differences in composition and location within the star system highlight the diversity of planetary formation and evolution. The formation of planets is influenced by several key factors, including temperature, distance from the parent star, and chemical composition. Temperature plays a crucial role in determining which materials can condense and accumulate during the early stages of planetary formation. Planets that form closer to their star experience higher temperatures, favoring the creation of rocky terrestrial planets. In contrast, planets that form farther away encounter cooler conditions, allowing gases and ices to accumulate and leading to the development of gas giants or ice giants. The chemical makeup of the surrounding disk also affects the types of planets that can form, as the availability of elements like hydrogen, helium, and heavier compounds shapes their structure and atmosphere. Together, these factors interact to produce the diverse range of planets observed in our universe. Observations from telescopes and spacecraft have played a crucial role in confirming theories about planet formation. Advanced telescopes allow scientists to study distant star systems, capturing images of protoplanetary disks where new planets are taking shape. Space missions, such as those conducted by the Hubble Space Telescope and various interplanetary probes, provide detailed data on the composition and structure of planets and their moons. These findings reveal patterns and processes that align with predictions made by planetary formation models. For example, the discovery of exoplanets in various stages of development supports the idea that planets form from clouds of dust and gas around young stars. Such real-world evidence helps refine our understanding of how planets emerge and evolve throughout the universe. The process of star system formation begins with vast clouds of cosmic dust and gas drifting through space. Over time, gravity causes these particles to clump together, forming dense regions known as protostellar cores. As these cores collapse, they ignite nuclear fusion, giving birth to new stars. Surrounding the young stars, remaining dust and gas gradually coalesce into disks, where intricate interactions lead to the formation of planets, moons, and other celestial bodies. Each stage involves countless physical processes, from turbulent collisions to chemical transformations. The complexity and precision of these steps highlight the remarkable nature of the universe, where seemingly random particles organize themselves into harmonious systems. This self-assembly showcases both the intricate laws of physics and the awe-inspiring beauty of cosmic evolution. The process of star formation holds significant meaning for our understanding of the origins of Earth and other planets. By studying how stars and their surrounding planetary systems develop, scientists gain valuable insights into the conditions that led to the birth of our solar system. This knowledge helps explain the distribution of elements and the formation of planets from cosmic dust and gas. Understanding star formation also sheds light on the potential for life elsewhere in the universe, as similar processes may occur around other stars. Ultimately, exploring these cosmic origins deepens our appreciation of Earth's place in the vast expanse of space.